Good morning, and this is Mrs. Moret here to help you with your review for the Unit 4 end of unit assessment. In this last part of the unit, you learned how to solve for an unknown exponent, and you learned about logarithms and different types of exponential and logarithmic functions. So in general, why do we need to know about logs? Well, sometimes we need to find an unknown exponent. So if we had something like, I don't know, let's say 2 to the x is equal to 16. Well, that's not a time where I would really even think about using logarithms because 16 is a power of 2. So I know, let's see here, 2, 4, 8, 16. So it takes 4 times of multiplying 2 to get 16. So I know 16 is really just 2 to the 4th. So if 2 to the x is equal to 2 to the 4th, then x must be 4. However, let's say I was trying to find 2 to the x equals, I don't know, maybe 17. Well, 17 isn't a power of 2, and so this is a time where I would use logarithms to solve, understanding the relationship. So if we're looking for an unknown exponent, then we can convert to log form and we have our value. So to convert this to log form, the base of the exponent 2 becomes the base of the log. So I move the 2 over by using logarithm. And so x is equal to log base 2 of 17. All right, so two different ways to solve exponential equations. But only one of those examples would be a time where I would use a logarithm. And this is the actual answer. This is the exact value. All right, so let's get started with the review. So first of all, explain why log base 10 of 8,500 is more than 3 but less than 4. And so for log base 10 of 8,500, there is some value x such that 10 to the x is equal to that 8,500. Well, I know the powers of 10. I know 10 to the third is equal to 1,000. And I know 10 to the fourth is equal to 10,000. And the reason why I chose to think about those two values is this 8,500 is somewhere between 10 to the third and 10 to the fourth. So that means the exponent needed to raise a base of 10 to 8,500 is a value between these two exponents, more than 3 but less than 4. So on number 2, for log base 2 of 20, it's the same sort of thinking. So my base is 2. I know there's some value, x, such that 2 to the x is equal to 20. And we just saw up here, 2 to the fourth is equal to 16. So 2 to the fourth is equal to 16. 2 to the fifth, the next power of 2, is equal to 32. And that value, 20, is between 16 and 32. So that means this x value is going to be between 4 and 5. So more than 4, but less than 5. All right, the next section, we're just changing forms back and forth from exponential to logarithmic, or logarithmic back to exponential. And so just keeping in mind the base of our exponent is the base of the log, and the base of the log will be the base of the exponent. So for 2 to the fifth equals 32, that means log base 2 of 32 equals 5. So notice that the 2 and the 5 are together in exponential form, and so they are separate in logarithmic form. They're not on the same side of the equal sign. All right? Okay, so we've got 3 to the fourth for the next one. So the base is 3, the exponent is 4, and that's equal to the 81. Here, when the base of the log is not written, then the base is 10. So I'm just going to put a little 10 in here. And so what I know now, this is my base, this is my exponent. So 10 to the fifth is equal to 100,000. And then finally, 5 squared equals 25. So we've got our base and our exponent on the same side of the equal sign over here. They're going to separate on the other side. So log base 5 of 25 is equal to 2. All right, so our first story problem here, it's a half-life problem, and it's being presented in a way you haven't really seen. Usually we'd use a factor here of 1/2, but instead we have a factor of 2 with a negative exponent. So just remember, like those negative exponents, that means that you're really dealing with a fraction, right? Negative exponents make fractions. So this 2 to the negative w, we're going to leave it this way, but I just want you to remember this would be equivalent to 80 times 1/2 to the w. That negative in front of the w would make the base of 2 actually be 1/2. But like I said, we're going to keep it this way and solve our problem in this manner. So this is the function for the half-life. The original amount is 80. And it takes about a week for the half-life. So without using a calculator, write an expression to represent the number of weeks we're going to be solving for W until there are 8 grams of this uranium remaining. So that means our function 80 times 2 to the negative W, we're going to set it equal to 8. So 2 is our base, negative W is the exponent. So the first step is to divide by the 80. And when we do that, we get 2 to the negative W. 8 divided by 80 is 1/10 or 0.1. Okay, so the exponent and the base all by themselves. So I'm going to move the base of 2 over. To do that, that means I'm going to switch to log form. So my next step looks like I'm going to write it over here. Negative W equals log base 2 of 0.1. Okay, and we're almost done. We need to get W by itself. So right now it's negative W. So negative W, same idea as negative 1 times W or negative 1W. And so to get the W all by itself, we're going to just divide by that negative 1. All right, so final answer, W equals negative log base 2 of 0.1. All right, ready for the next page. Okay, so we have an equation, P of W equals e to the W, which represents the population of a mold sample, W weeks after it was initially counted. Here's a graph. Use the graph to answer the question. So this is the graph of y equals e to the x, right? And of course, we're using P of W and W, but that's kind of the general, like that's what that graph represents, y equals e to the x. And so if we were to think about this in log form, when our base is e, we can use natural log. And so if y equals e to the x, then x is equal to the natural log of y. Okay, so if we want to know a reasonable approximation for the natural log of 500, and we could also write this as the natural log of y, then I'm going to find the 500 on the y-axis, and the approximation is going to be the x value. So here's 500, follow it over. Here it is where it touches the function. And then bring it down here. these are counting by ones on the x-axis. So 5, 6, I don't know, about 6.2. I'm just going to write about 6.2. All right, what does the natural log of 1,000 represent in this situation? So this value right here is 1,000, and then the natural log of 1,000 is, I don't know, it's really close to 7. And so what it represents in this situation is that in about 7 weeks, the mold population will be at roughly 1,000. Okay, so the natural log of 1,000 is approximately 7. And that means it will take 7 weeks. It's a very slow growing mold population. For the population to reach 1,000. All right, so again, we've talked a lot in class about really being able to communicate the meaning of the values in a graph or the meaning of the values in a function. And just remembering, like, math didn't just make itself. It was always created for a purpose. And so we have to think about when we have these problems in context, which is where the real math lives, that those numbers have some meaning behind them. All right, then we get to these problems here, which are just straightforward, show me you understand how to solve these equations. So in solving these equations, sometimes I would use logarithms and sometimes I wouldn't. It just depends on when we're solving for the unknown exponent, is the value we're looking for a power of the base or not? If it's a power of the base, I personally would not use a logarithm. It's like extra writing, to be honest with you. But anyway, so let's get to this. All right, so our strategy is always to start by getting the base and exponent all by itself. So we want to eventually get all of our equations into some sort of base to the exponent equals a value. And at that point, we can either determine the exponent because a is a power of b, or we can use a logarithm because a isn't a power of b. All right, so to isolate this 10 to the 2n, I would start this one by dividing by 9. And even though you can do this in your head, it's important that you're showing your work so I can see your full understanding of the solving process. 9,000 divided by 9 is 1,000. And so 10 to the 2n is equal to 1,000. Okay, so 1,000 happens to be a power of 10. 1,000 is exactly 10 to the third. So what that tells me is I can say, oh, well, 10 to the 2n is equal to 10 to the third. And so the 2n must be equal to 3 because if they have the same base, they have to have the same exponent in order to actually be equal. So if 2n is equal to 3, simply divide by the 2 and you get 1.5 or 3 halves. Either answer is great. Okay, on B, we're going to divide by 6 to get 10 to the m by itself. So 4,500 divided by 6 is 750. So 10 to the m is equal to 750. Now, 750 is not a power of 10, and so this would be a great time to use a logarithm. So we're going to move the 10 over by using a logarithm. So m is equal to, you can write log base 10 of 750 or just the log of 750 because when the base is not written, the base is 10, so you don't have to write a 10 there. And then this would be the exact answer. You can type the log of 750 into a calculator and you get about 2.8751. I guess I should put my calculator here so you can see it. Okay, so the log of 750, about 2.8751. All right, next one, 112 equals 7 times 2 to the k. So we're going to divide by 7. 112 divided by 7 is 16. So what I know now is 2 to the k is equal to 16. 16 is a power of 2, so I'm not going to use a logarithm. 16 is exactly 2 to the 4th, right? 2 to the 4th is 16. So I'm going to write 2 to the 4th. So again, if those bases are both 2, in order for them to be equal, their exponents must also be equal. So we've already solved for k. K is equal to 4. All right. Next, 5 to the 2x is equal to 125. 125 is a power of 5. It's 5 to the 3rd. See, 5 to the 3rd is 125. So that tells me 5 to the 2x is equal to 5 to the 3rd. And one more time, if their bases are the same, their exponents must be equal. So 2x equals 3. We've solved this before, right above actually. 3 divided by 2, x is equal to 1.5, or 3/2. All right, on E, we're going to get 10 to the x by itself by dividing by 2.5. And 250,000 divided by 2.5 is 100,000, which is a power of x. So that means if 10 to the x is equal to 100,000, well, this is 10 to the 1, 2, 3, 4, 5, which tells me, oh, x must equal 5. All right, and then finally for F, again, our first step, isolate the 10 to the m by dividing by 5. So 55,000 divided by 5 is 11,000. So 10 to the m is equal to 11,000. And 11,000 is not a power of 10. So I'm going to use a logarithm, move the base of 10 over, using a log. So m is equal to the log base 10 of 11,000. And that is approximately 4.0414. All right, so hopefully you can see the difference now between like when do you really need to use a logarithm to solve one of these equations and when do you not, because it's going to be a power of the base. All right. Okay, so moving right along, we've got a couple more story problems for the rest of the review. So next, some more mold. All right, so an expired loaf of bread was found with mold on it. This is a very realistic problem. The mold is growing exponentially according to the model. M of x equals 2 times e to the 0.088x, where m of x is the amount of mold covering the bread in square centimeters after x days. How much of the bread was covered when it was first found? So this 2 right here tells me when it was first found, 2 square centimeters of the bread was covered in mold. The 0.088 in this context, that's the continuous growth rate. So continuous, growth. But in this context, it tells me that the mold has continuous growth by 8.8%. Okay, so the mold colony is growing continuously by 8.8%. And write an expression for the number of days in which 8 square centimeters of the bread will be covered in mold. So I'm going to take the 2e to the 0.088x, set it equal to 8, and then solve for x. So that answer I get for x is the expression for the number of days, okay, because x represents the number of days. So now I have to get the x all by itself to be able to write that as an expression. All right, so our base is e, our exponent is 0.088x, and so start by dividing by the 2. So e to the 0.088x is equal to 4. Okay, so now we're going to switch to log form, and since the base is e, we will use log base e, also known as the natural log. That's what your calculator knows how to calculate, how to compute. All right, so our exponent, 0.088x, is equal to the natural log of 4. And the last step to get x by itself is to divide it by 0.08. Oopsies. Only 1/8, or only 2 eighths, not 3. 0.088 on both sides of the equation. And so my expression for x is the natural log of 4 divided by 0.088. That's the answer for part C. And then part D, use your calculator to evaluate the expression from part C. So I need to evaluate the natural log of 4. Remember to close the parenthesis before dividing by the value on the bottom, the 0.088. So we're looking at about 15.8, almost 16 days. So I'm just going to write approximately 15.8 days. All right. We have another similar problem, only this time it's going to be the balance of a savings account. What was the initial investment? What does 0.05 mean? And then when will we have a balance of $20,000? So it looks like our initial investment is $1,500. The 0.05 is, again, the continuous growth rate. In this context, it means that the account is growing or grows by 5% continuously. Okay, so these functions that involve E, the natural base, those are continuous growth or continuous decay functions. So that's how I know it's happening continuously. All right, an expression for the number of years it will take for the account to have a balance of $20,000. So same thing, we're going to take the 1,500 e to the 0.05x and set it equal to 20,000. And so we'll start by dividing by the 1,500. And when I do that in my calculator, 20,000 divided by 1,500, notice I get this repeating decimal. And that's just not good to round right now. We're not done with the problem yet. This is a horrible time to round. So I could either leave it as that fraction, 20,000 over 1,500, or I could just ask my calculator to reduce the fraction. Math, enter, enter. It's 40 thirds. All right, so I can go either way. So when I divide this here, this is exactly 40/3, just reducing the fraction. Okay, so that means, okay, so we have gotten rid of that. We have this e to the 0.05x by itself. It's equal to 40/3. I'm going to use that just because it's smaller. All right, we're ready for natural log, right? To move the e over using the natural log. And so, gosh, I don't have enough space. I'll just do this. Okay, so I'm going to go from here up to here. So no, just kidding. Okay, so I'm switching forms. So 0.05x is equal to the natural log of 40/3. And now divide. Okay, so x is exactly the natural log of 40/3 divided by 0.05. And so putting that into the calculator, the natural log of 40/3, close the parenthesis, and then divide by 0.05, and you get about 51.8. So about 51.8, almost 52 years. So about 51.8 years. Okay, so this is the final answer for the expression, right? This says write an expression. It doesn't say to find the actual value. It says write an expression. So this is the expression. And then on the review, it does say to use your calculator to evaluate the expression that you got. Okay, so this is definitely necessary when the directions ask for an expression. That might be a really big hint to you guys because you're going to be asked to write an expression. This is the expression. This is the value once you've evaluated, but this is the expression, approximate value. Okay, enough of that. Let's move on and finish the back page. Oh, we have one of those graphs where they're going to cross. Oh, it's about bees. So Bert is a beekeeper. He already has a bee colony that is doing quite well, but he wants to try a new type of bee box that is supposed to help the bee population increase more quickly. Bert is going to measure the difference between his established colony, colony A, and the new colony, colony B. Both are shown in the graph. Okay. The approximate coordinates of the point of intersection of the two graphs, what does this mean in terms of the two bee populations? So here's where they intersect. And I would say, let's see, the x axis is counting by ones. This looks like it's right at 9. And then on the y-axis, it's counting by like 10,000s. So I'm going to say like those coordinates are about 9. And then 48,000 is my estimate for the y value. Okay, but in context of in terms of the two bee populations, so the 9 represents the time in weeks, the 48,000 represents the bee population. So I'm going to say after 9 weeks, both populations have 48,000 bees. All right. A response like it's where they're the same would be a level 1 response. A response like this that uses details and is specific would be a level 4 response. Okay, so choose what you want. I know you want those level 4s. All right, B, the population of colony A is given by the equation y equals 30,000 e to the 0.05x. When will this population reach 100,000? Explain your reasoning by showing your work. So this is about population A, which starts at 30,000, is not increasing as quickly as population B. So I can't just like use the graph to estimate because it's going to be way off the graph. So we're going to go ahead and set up and solve an equation. So 30,000 e to the 0.05x is equal to 100,000. Okay, we start this by dividing by the 30,000. And I'm just going to reduce the fraction over here. So let's see, 1, 2, 3, 4, and 1, 2, 3, 4. This is just 10/3. Okay, so now I know e to the 0.05x is equal to 10/3. And I'm going to get the 0.05x by itself by using the natural log. So 0.05x is equal to the natural log of 10/3. And now I'm going to divide by 0.05 on both sides. Okay. And so I'll use the calculator. The natural log of 10/3 divided by 0.05 is 24.079, 24.1. So I'm going to say about 24.1, and these are weeks. All right. Last two questions. So first of all, the graph of y equals log base 2 of x, our base is 2 here. Explain how you know the point 2 is on the graph. So the point, 4,2 is on the graph. And so when I'm looking at this, I'm thinking to myself, okay, so this is the x value. This is the y value. Oh, that looks like an x, but y. So I put them in the place of x and y in the equation. Is this a true statement? So y equals, does 2 equal the log base 2 of 4? The log base 2 of 4, I can rewrite that in exponential form. This is our base. This is our exponent. So this is true. 2 to the second is equal to 4. So I know that 4,2 is on this graph because, again, substituting the values into the equation, 2 is equal to log base 2 of 4. I know 2 to the second is equal to 4. This is a true statement, both of them. So that's how I know it's on the graph. What is the x-intercept? How do you know? So let's see here. The x-intercept, that's when y is equal to 0. So what we're saying is, when does log base 2 of x equal 0? Okay. Well, guess what, guys? 2 to the 0 is equal to 1, right? So that tells me if I switch this to exponential form, 2 to the 0 is equal to x. This is our base. This is our exponent. 2 to the 0 is equal to x. And 2 to the 0 is 1. So the x-intercept, x is 1 when y is 0. So the x-intercept is 1, 0. Okay. Will the graph meet the line y equals 10? Explain how you know. Will the graph meet the line y equals 10? So the question is, will this graph, log base 2 of x, will that ever equal 10? Well, yes, it will. Because again, we can just switch forms. We kind of did this in class the other day. We can just switch forms. Move the 2 over. It's now the base of an exponent. So x is equal to 2 to the 10th. So the answer here is yes. When x equals 2 to the 10th. And 2 to the 10th is 1024. Okay. All right. And the last question is very similar type of question. Here's the graph of y equals log base 5 of x. So this time the base is 5. Explain how you know the point 125.3 is on the graph. Again, we just plug this in for x and this in for y and verify that it's a true statement. So y equals 3 equals log base 5 of 125. And switching that to exponential form, this is our base, this is our exponent, 5 to the third, is equal to 125. You can even put it on your calculator, 5 to the third is equal to 125. So we can verify that yes, for sure, that is a point of the graph, or on the graph, okay? These are both true statements. What is the x-intercept? How do you know? So we're going to solve the same sort of equation. When does log base 5 of x equal 0? That happens when x is 5 to the 0, which is 1 again. And so our x-intercept, x is 1 when y is 0. And then finally, will the graph meet the line y equals 5? Explain how you know. So we're looking at log base 2 of x. Will that equal 5? Again, yes, it will. Oh, not base 2. Sorry about that. Base 5. Log base 5 of x. Anyways, yes, it will as well. So we just switch forms, move the 5 over. It's going to be the base of the exponent. So it will when x equals 5 to the 5th. So our answer is yes when x equals 5 to the 5th. And 5 to the 5th is 3,125. And so both, it's yes again for that reason. All right, so this review covers everything that's on the test. We'll be going over questions in class on Monday. So make sure that you get through what you can, and then I'll see you in class on Monday and help out with any of the questions that you still have. All right, enjoy the rest of your weekend.